So let's start off from where we left off, which was we mentioned that this much part of the system is kind of same as the CPU from our model here, right? And so the question now is that we want to dive a little deeper into what's going on here. So let's go back here and let me propose the following. So we now want to focus ourselves on the CPU and then kind of, go from there. So to be able to understand what a CPU is in terms of like as seen by the software, we have to work with something called, the programmer's model of the CPU. Right. So again, I just have to reiterate that we are intending to see the usage or the importance of this, and we are right now trying and reason about the programmer's model of CPU, which is, how should a software engineer think about the CPU, right? Okay. So for this, we have to briefly talk about storage, which is interesting, right? So we are now going to talk about storage. So imagine how one bit might get stored. One of the ways to store it is, take a capacitor, and this is like the ground terminal here. Take a capacitor and dump some charge on it. So if the charge exists, you call it 1. If the charge doesn't exist, if the capacitor is completely discharged, you call it a 0. Fair enough. The other way to think about it is think of an inverter. So if you give a 1, it becomes a 0 here. And you can think about a feedback circuit wherein if you provide like a 1 here, it becomes a 0 here, that 0 comes here and becomes a 1 here. So kind of whatever value you provide here, let's say, is trapped in this circuit. And as long as the power is available, we can say that if we had a circuit like so, from where we read the value, kind of inferred the value, this would read as 1 because this is 0, right? So we can then say 1 is trapped in a feedback, in a loop, in a circuit. And now here what can happen is in this situation, the charge can dissipate or discharge over time. And that way we lose the value, lose the memory, so to speak. But in this case, we won't as long as the power is on. So then let's move forward, assuming that bits are stored this way, just as again as a mental model, right? A way to think about things. So then we take this, draw a box around it, and call that like 1 bit of memory, right? And now if we take a lot of such bits next to each other, and let's say we take 8 bits, and let me just draw that out real quick. So we have the 4, yeah. So we have, let's say, bit 7, bit 6, bit 5, bit 4, bit 3, bit 2, bit 1, and bit 0. So these 8 bits, so to speak, which you're supposed to imagine like so, for our purposes, we call this entire bunch a register, right? And then if we have a value like 1011101 represented, we say that this register is representing an 8-bit value. Okay. Okay, so now we then call this an 8-bit register. So what I now want you to imagine is that this register, instead of being 8 bits, is actually 32 bits. So once you have made peace with this idea, and again, trust me on what's happening here. We are slowly moving towards understanding the CPU, the programmer's model of it, the the role of NVIC or interrupt controller. We'll come to all of that. But just hold in your mind this information that the unit of storage is a bit. A bit can be represented like so. And then, this box here is essentially this circuit. We are then, moving forward and calling bunch of bits grouped together as a register. Register can have a width. This is 8 bits register. And then I'm asking you to imagine bits clubbed together and 32 of those, and then this is a 32-bit register. Now obviously there has to be some electrical way in terms of which values get loaded to it, then that value is kind of put in a feedback, and then there is some way to read it, so on and so forth. Let's not worry about those mechanisms. They exist in hardware, but let's not worry. We'll just assume that this register can be read and written too. All right, and so we were like this backstory or this side discussion, this detour, so to speak, was important because the programmer's model is based on the idea of registers, and that is why this concept is important. That is why I was mentioning to you that the idea of registers is what will help us understand things. Okay, perfect. So now you can also reason that if we had, let's say, and this is actually how I think about things, and it has always worked for me. So let's say we have registers that are 8-bit wide and which are kind of, stacked together. So this is like register 0, this is register 1, register 2, so on and so forth. And if you have like an array of these 8-bit registers, then the idea is that you can call it memory, right? Because I also mentioned that a bit is a unit of storage, unit of memory. 8 bits is what we can read and write to. 32 bits is what I was nudging or hinting towards. So then in this case, if we had 8 bits worth of register and many of those in an array, then we can call that a memory. And now this again is a slight detour, but this is like model of memory, so to speak. So each register can then have a number 0, 1, 2, 3, 4 as an address. And so in our previous model, then the CPU, when it was floating or sending over the address, you can think of it as it is sending a number that represents the register. And then the value either comes back or the value is being written to, right? So hopefully the idea of memory somewhat is clear to you now, how to think about memory. And now interesting thing is, we'll also mention that in the memory, we can always access data 1 byte at a time. You can read one register at a time. You cannot read 4 bits. You cannot read 2 bits. You have to read or write 8 bits. That's the granularity, so to speak. Okay. So then back to this topic, I was mentioning that programmer's model is built on the idea of registers. And so we'll move forward. And now let's talk about how a CPU is to be seen by a programmer. And so now my claim is, and we'll dive into the details in a bit, maybe in next video, but my claim is a CPU, as seen by a programmer, as seen by a programmer is, is just bunch of registers. That's all. And this is the key idea. If there is anything that you can take from this video or you'd like to remember, that would be this. A programmer's model is bunch of registers, right? Okay, so back to the CPU. My claim is that we can think of the CPU as bunch of registers And as we manipulate those registers, the CPU does something, right? So let me just abstractly talk about things and it will become a lot more clearer. So there are few registers that are called GPRs, general purpose registers. These are the registers that will hold the value of your computation, adding two numbers. Uh, so the number to be added would be, let's say, these are referred to as like R1, R0, R2, so on and so forth. So let's say you're doing R2 equals to R1 plus R0. So that means take the data that is in R0, add it to R1, and put it in R2. But this is like registers. So you load R0 with some value, R1 with some value, and then issue an instruction saying, hey, add up two numbers and add numbers that are in R1 and R0 and put the answer in R2. So the CPU's state, so to speak, the state information, what the CPU is doing and how to influence it is all kind of controlled and guided by registers. And so there is GPRs. Then there are some registers for status. For example, did the addition come out to be negative number? Did the addition come out to be like a zero? Did the subtraction come out to be zero? All of those are kind of those states are represented by values of different bits in some registers, and those are called status registers. Then there are certain other registers which kind of control what the CPU can do, and those are called the config registers. So far, what have we done? We talked about the model of a bit, then we expanded it to the register. From register, we went to the memory, and then I kind of came back and revisited how to think about CPUs, and my claim was CPUs are a bunch of registers as seen by a programmer, and that's called the programmer's model. And we'll revisit this idea again and again. It's so fundamental. If there is anything to remember, remember this one statement. Programmer's model is a bunch of registers that represent and control the state of a hardware. Hardware in this case is the CPU. So how did we come here? We were talking about the role of NVIC here, and then we said, oh, okay, let's talk about what a CPU really is, as seen by the programmer, and the answer to that was a bunch of registers. And now let's talk about the NVIC here. And NVIC is for the ARM M-class CPUs, it stands for Nested Vector Interrupt Controller. And every M-class CPU has this. So pretty much what you learn next applies to M0, M0 plus, so on and so forth. And also we haven't talked about what qualifies as an M-class CPU, what are the different variants. We'll come to that as well. But for now, M-class CPU comes with an attached or integrated NVIC, which is nested vector interrupt controller. Let's go back to that. And the whole discussion about registers, by the way, is also useful when we talk about NVIC. And as I was mentioning, there are certain registers that do the configuration and control what the CPU can and cannot do. Similarly, there are a bunch of registers that will control what the NVIC can and cannot do, and we'll come to that in a bit. All right, so back to our whiteboard here. Let me scroll down and start fresh. Okay, so we previously, in previous videos, kind of, talked about the CPU, buses going to the memory. And now we can also imagine, how that memory is to be interpreted or imagined about, like an array of registers. So let me just call this memory. Then there was like a data bus, instruction bus, so on and so forth. We said there were a few GPIOs, and now there were also interrupts. And very carefully listen what follows. If your system was to have 128 interrupts, let's say, right? Your CPU is attending to some signal that's coming from the engine. It's tending to some signal that is coming from, I don't know, some buttons in the car. Maybe, it's sensing the temperature in the car and so on and so forth. And all of those are supposed to be interrupts. Then the straightforward, model is that we would need 128 128 pins on that CPU that are to be tied to or connected to. That's another way of, like, tied to is another way of saying that they are connected to, temperature sensor, engine, some signal, oil, whatever level, tire pressure, so on and so forth. The system needs to, the CPU needs to have 128 lines dedicated to these external input sources. And now here's the thing. Each pin on the CPU, it is expensive. When you're designing a CPU, the least number of pins, uh, sorry, the cost of the CPU or the manufacturing cost of the CPU depends on how many pins you want to bring out on this package. This is the package, the black color thingy of the IC. The more number of pins you want, the more expensive and complicated the manufacturing process is going to be. So what people tend to do is they tend to kind of reduce the number of pins that are going to be used for interrupts. And so now what happens is we have our CPU here. We say, okay, again, it has got like buses here, um, uh, different buses, memory, so on and so forth. And you had few inputs here, let's say 32, pins. What the M class folks have done is they have given another IC, another integrated circuit that kind of has one line going to the CPU and one bus going to the CPU, one or bunch of them, right? And kind of there are few more wires going from the CPU as well, which we'll come to later. And then the idea is that this IC, all the pins on it would be dedicated to interrupts. So instead of like the CPU having too many pins, we reduce the number of pins on the CPU, so the CPU can be as tiny as possible. And then next to that is another circuit where the only thing coming out of that circuit is a lot of, so to speak, lines that are available as interrupts. So now what happens is, and this is called the interrupt controller. Well, IC stands for integrated circuit. In this case, we are going to call it interrupt controller, right? So what the interrupt controller does is it kind of exposes lines to the external world, and now your different things can kind of connect here, and kind of is the keyword because again there's like a little bit of magic involved. So this comes as one package now, and these are going out. Okay, so the interrupt controller is what is handling the incoming interrupts, and then it will kind of just pass to the CPU a signal that, hey, an interrupt happened, looks like 25th line here is active, and that number 25 gets kind of passed on a bus. So the idea then is the CPU is having only one line dedicated to the interrupt, and the interrupt controller is kind of giving out many more lines from which it takes the inputs and it juggles or handles, not juggles, but it handles the incoming interrupt related information, right? So if number, your device number or the peripheral number, let's say your fuel gauge, fuel level is a problem, then the indication for that comes on like number 25 interrupt. That goes to the interrupt controller. The interrupt controller records that number 25 because it knows which line has kind of hinted at, or which line was activated. So it says, hey, 25 and then I must tell the CPU. So the CPU kind of is interrupted now. The CPU says, oh, okay, you know, what interrupt happened? Number 25. Okay, I must go do something about number 25. So the M class CPUs then have this interrupt controller inbuilt or integrated. Right? So if you see here, yeah, so there is this bus going, then there are some lines coming, right? And as part of this bus, there is also line going to the Cortex-M processor, and that is the actual, so to speak, interrupt line. And then what you see on this side is all the peripherals are connected as IRQs. IRQs is nothing but interrupts. And the NMI here is also an interrupt. It is just like a special thing which is called non-maskable interrupt. If this interrupt happens, for example, if the engine is completely screwed, well, then the processor must go and kind of, do something like break the car or, glow a light, do something, right? And this interrupt cannot be ignored, so to speak. And we'll come to that part in a bit also. So this NVIC here is called the nested vector interrupt controller. And why it is called the nested vector interrupt controller, that is like a separate topic. We'll come to that in another video. But what I wanted to convey as part of this video is this and this together is the M class CPU. I mean, you can think of it that this interrupt controller, the role it plays, that's what I wanted to call out. Okay, so the other thing now is the configuration registers. Right? Let's come to that. Let's say for whatever reason, we wanted to tell this NVIC that, hey, yeah, you can handle 128 interrupts, you can, give out those many lines, and other hardware can signal to you that they need attention by raising the interrupt line. But you know what? We would just want you to report to the CPU, so to speak. Just report to the CPU only interrupts between 0 and 10. And in certain cases, we might be like, hey, when the line number 8 goes from 0 volt to 1 volt, only then report it. And in certain other case, let's say line number 9, when it goes from high to low, 1 to 0, so to speak, only then report it. So where are we going to pass information related to this? And also the fact that 11 through 127 need to be ignored. So the idea now here is that there are certain registers within NVIC that can be written to, and how to write them, again, separate topic, we'll come to that. But if they are written to, then we say that the NVIC can be configured. NVIC can be programmed to ignore an interrupt, to pass an interrupt only when the line goes from 0 to 1, the line goes from 1 to 0, so to speak, edge triggered, level triggered, so on and so forth. So that is what is represented here as the configuration registers. And again, now this is very interesting, because if you were to think, the config registers will be called the programmer's model of NVIC. So this is like a constant theme in embedded systems. Any hardware that you're working with, that you're supposed to kind of program in your code, the first question to ask is, hey, do I have a programmer's model for this? And typically you will have. What happens is any hardware, whether it's, UART, and UART is like a hardware, whether it's SPI, PCIe, whatever, any hardware will be presented to the programmer as a bunch of registers. And if you write those registers, certain settings are configured. And when the inputs and outputs need to be kind of read and written, when you want to see what came through the UART, you just read one of the registers. When you want to send some value out, you write to one of the registers. So the registers are really programmer's model. Any hardware that you're working with, please ask for the programmer's model and things fall apart. So hopefully you're convinced about NVIC, the programmer's model. Again, we just touched upon what programmer's model for the CPU means. We'll dive into the details. We started off with a bit, the idea of a bit, and all the way from there we have kind of also understood what the role of an NVIC is. And in the next video, let's kind of dive into what the other thing here is, the SysTick, and then we'll kind of move forward towards architecture of the M-class CPUs, the variety of those, the different CPUs, and so on and so forth. So I'll see you in the next one.